Assalamualaikum and greetings. My name is Ahmad Zafar Mustafa Kamal. I'm going to talk about our third lab session, which is the state space representation. For our objective is to find a mathematical representation called a state space representation for an electrical system. And the second objective is to implement and analyze the system response of control system obtained from state space function. And for the methodology, for part A state space modeling technique, we are supposed to analyze, we need to find the unit state output from the electrical system, which was from the figure 1 here, by using the finite space state space representation by using the state variable, which should be as shown here. And for part B is to convert the state space to a transfer function. And lastly, we're going to discuss and conclusion of our findings in the report.
So for this, we have three state space representation for the figure part A. I've used two main equation, which is C dV C1 over dt C1 equal to I C1 and L dIL over dt equal to VL, and C2 dV C2 over dt equal to I C2. We have assumed that capacitor and inductor equal to 1. This circuit, we're using a nodal analysis. Using the KCL and voltage laws, we have used the equation which is IC1 equal to IL plus IR, and then we solve it equal to minus VC1 over R plus IL minus VC2 over R plus VL over R for the equation 1. And then we use the VL equal to VT minus VC1. After that, we use the equation IC2 equal to IR equal to VL minus VC2 over R. We solve the mathematical equation and get the negative VC1 over R minus VC2 over R plus VL over R. Then we substituting this relationship into equation 1 and use this equation C1 dV C1 over dt equal to minus VC1 over R plus IL minus VC2 over R plus VL over R, and get the dV C1 over dt. After that, we use the L dIL over dt equal to VT minus VC1 and get the dIL over dt. After that, we use the C2 dV C2 over dt and get the dV C2 over dt, which is minus VC1 over RC2 minus VC2 over RC2 plus VT over RC2. And we putting the equation into the vector matrix form. So we have arranged the equation into 1 over RC1, 1 over L, and 1 over RC2, and get the output, which is y equal to 0, 0, 1 and x1, x2, x3. For the MATLAB equation, for the part A, we have stated that C1, C2, L, and R equal to 1, and stated A into the matrix forms. We declare the B, which is 1 over R times C1, 1 over L, and 1 over R times C2, and C, which is 0, 0, 1, and D doesn't have the input, so we assume 0. After that, we created a Simulink, which is source, gain BU, add, and gain A times U, integrator 1 over S, and gain C times U, which is Y equal to CX, and things, which is scope. After we run it, we get the stable equation, because stable signal, which is this signal, tends to go to 0, and T tends to go to infinity, which is stable. We can verify this signal, and using the MATLAB code, we can find the same signal as we find at Simulink. We're using command EIGA, and then we're using command numerator and denominator for the SS to TF for A, B, C, and D. And we using command G equal to TF, numerator and denominator, and stat G. After we run it, we can get the poles, which is 3 of the poles is negative. If the poles is positive, the signal is not stable. After that, we can get the numerator and denominator and get this transfer function. This is for the open loops. Next, we can get the signal, and the characteristic that we choose is steady state, settling time, and rise time. Find the open loops using this command, which is t equal to feedback g1 and figure 2 and step t function. So we can compare the figure 1 and figure 2 from the open loop and closed loop. This is the figure 1 and the figure 2. So we have choose the figure 2, which is exactly the same as the signal in the Simulink.
In part B, for the calculation, first we need to convert the state space into the transfer function. First step, we need to identify the state variables A, B, C, and D. In this case, A is equal to this matrix, while B equal to this matrix, and C equal to this matrix, which is we can get from the output, while the D is equal to 0. And then we need to find the value of SI identity matrix minus with A. So after we put the value into this form, we will get the result as this matrix. To get the inverse matrix for this form matrix, we need to use this equation, which is SIA minus with A matrix inverse equal to adjoint SIA minus A matrix divided by determinant SIA minus A matrix. So next, we need to find the determinant first. After we do the calculation for the determinant, we will get the result as S power of 3. The determinant result as S power of 3 plus 2 S power of 2 plus S plus 1. So for the adjoint adjugate of Si minus A matrix, we need to find the value for the H position, which is C11. We need to find the determinant. We need to do the determinant for each position, which is C11, C21, C31, C12, C22, C32, C13, C23, and C33. After we do the calculation, we put into the formula, we will get the result as adjugate Si minus A matrix as this matrix. So to do the inverse, we need to change this line into this row, which is first line into the first row, and follow with the others. Divide by the determinant, result for the determinant. After substituting the inverse Si minus A matrix, B, C, and D into the transfer function matrix. So we put this value, this variable, to get the transfer function, this formula. So after we do the calculation, we perform the calculation, we will get the transfer function as this: S power of 2 divided by S power of 3 plus 2S power of 2 plus S plus 1. In the coding for the MATLAB, in the first line, we need to declare the variable, which is we use sims S. And we also need to declare the variable for the matrix A, the matrix B, matrix C, since in this case, matrix D is equal to 0, so we didn't have to declare in this MATLAB code. Next, we declare Si equal to S multiplied by I3, since we use, in this case, we use 3 by 3 matrix. And after we run this code, we get the S identity matrix as this matrix. Next, we need to declare SIA equal to S identity matrix minus with A, which is after we run this code, we get the matrix as this matrix. Next, we also need to find the inverse matrix for SIA matrix. We put this value SIA inverse equal to inverse SIA matrix. After we run, we get this. Same with in our calculation. Next, after we get the inverse of this matrix, SIA matrix, we also need to find the adjoint SIA matrix, which is we use this code adjoint SIA equal to adjoint SIA matrix. And after we run, we will get the adjoint matrix for SIA. Next, after we find the value of adjoint SIA matrix and determinant SIA matrix, we can do the equation for the inverse matrix, which is SIA inverse 2 equal to adjoint SIA matrix divide by determinant SIA matrix. And after we run this code, we will get the inverse SIA matrix, which is this matrix. Just after we get this result, we can find for the transfer function, which is we use this code G equal to C multiply by SIA inverse 2 matrix, multiply by B. After we run this coding, we will get the transfer function result. For plotting the transfer function response, we need to declare the numerator as 1, 0, 0 and the denominator as 1, 2, 1, 1. To finding the equation, we need to use this SYS, SP, TF numerator and denominator. After we run this code, we will get the value for the transfer function. And in this, for the coding, figure 1, we need to plotting the graph for the transfer function response. Step SYS, SP and green on. So the result we can see here, the result for the transfer function response. So in this graph, we can see the peak amplitude 0.353 and the rise time 0 equal to 0 and the final value is equal to 0. And in this graph, we can see the signal, the transfer function response is stable.
So for conclusion, within the part A, state variable xt can be reconstructed from the measured input-output data, but are not themselves measured during an experiment. The state space model structure is a good choice for accurate estimation because it requires you to specify for only one input the model order n. And for the comparison of transfer function and state space model, they are mathematical model describing the behavior of the dynamical system. Thus, these two are not physical but mathematical entities. Still, there are a lot of important differences which, for some of it, is transfer function is not defined for nonlinear system, and thus can only be described linear system. However, state space model can be described both. And next, transfer function can be described the dynamic between single input and single output, namely, it transfers the input to the output. For multivariate case, where system with multiple input or outputs, it was needed to resort to transfer function matrices where the elements of the which are individual transfer functions, and things start to get somewhat hefty. On the other hand, the state space model is rarely appropriate for the multivariate case since it keeps track of all input, state, and output that are included in. That's it from me. Thank you.